I think it's time. Thank you so much for coming back so punctually. We will be continuing with our artistic side of Code Dive. And the next person to speak is Guy Davidson. He's the head of engineering at 6 Impossible Things Before Breakfast, where he attempts to make the impossible possible. He's also a member of the C++ Standards Committee and the chair of programming languages for the British Standards Institute. A former radio presenter, Guy also sings first bass for the Brighton Festival Chorus and has played the Mrs. Mills piano at Abbey Road. Let's have a quick look, shall we? So this is Miss Mills, for those who are not familiar with very old English music. She was a pop star at some point. Okay, this is the piano at Abbey Road. You might remember Abbey Road from the Beatles' famous record. So that's the actual piano. And this is Guy playing the piano. Other than that, it is portable floating point calculations. Let's put our hands together for Guy Davidson.
Right, come on, you can do this. Excellent, yes you can, thank you. Hello everyone, my name's Guy Davidson, as you heard. I played Lady Madonna on that piano, which was written in that room. Most of the Beatles songs in the mid to late 60s were written on that piano, so I just had to play it. Here's our agenda. We're going to be talking about non-integral values, standardizing non-integral arithmetic, standardizing C++ for non-integral values, and improving reproducibility of non-integral values. This was a 1-hour talk. It's now a 45-minute talk. Yes, we can do this. Right, non-integral values. So let's start with our arithmetic operations: addition, subtraction, multiplication, and division. Each of the inverse functions, subtract and divide, can create results outside of the original domain. So for example, addition on natural numbers will keep you in natural numbers, whereas subtraction on natural numbers will sometimes take you to the integers. Multiplication will keep you in the integers, division will put you into the rational numbers. And rational numbers are ratios. The clue is in the name. They are countably infinite, which I find quite exotic and lovely. I'm actually a mathematician more than I'm a computer scientist. Half of the rational numbers lie between -1 and +1, which I also find extraordinary. They're very analog. There's something of the cosmos about them. They're delightful. Every 2 rational numbers has another rational number between them. And they're reducible via the fundamental theorem of arithmetic, where you can factorize prime numbers and do cancellations and things like that. Has anyone here used a slide rule? You should all go and buy a slide rule and learn how to use it and get in touch with the true center of the universe. So yeah, I like rational numbers until, of course, I have to add them. Adding rational numbers, very unpleasant. Multiplying is easy, but with addition, you have this cross-multiplication going on. You know how to multiply fractions, you know how to multiply rational numbers. You can tell that it doesn't take long for things to just get too wide. Once you've started adding 30 or 40 of the things together, you overflow horribly. And factorizing is a rare opportunity. Having coincidentally matching prime factors is actually quite unusual as things get larger. You might think you might use an arbitrary sized integer class to represent things, but then you've got the same problem. You're running out of space all the time. Hang on. There we are. And it increases the time to compute. It takes up memory. You can't just say to your clients when they ask you, well, how long will this operation take? You can't just say, well, it depends. They don't like that. But we came up with a solution quite a while ago. And it depends on who you ask exactly when. Decimal fractions have been used for several thousand years. But if you're familiar with the decimal point, and I hope you all are familiar with the decimal point, this turned up in a book by John Napier on constructing logarithms. It was published at the beginning of the 17th century. Now, the decimal point tells us that we are now approximating via sums of powers. The final digit after the decimal point, sorry, the first digit after the decimal point, gives us the number of tenths, the next the number of hundredths, and so on. By adding more and more negative powers of 10, precision can be improved, but there are only a small set of numbers which can be represented exactly, because since we're in base 10, the prime factors are 2 and 5. The only rational numbers that could be represented exactly are those whose denominator is representable as a product of powers of 2 and 5. So for example, 1/8 is 0.125. 3/40ths is 0.075, or 75 thousandths. And other numbers, though, aren't so lucky. In fact, most numbers aren't so lucky. Here's 1/7. This is represented as 0.142857 recurring. But I got this when I asked Clang to show me what 1/7 is. And as you can see, it's quite wrong. All numbers that are not exactly representable will recur over a maximum of 10 to the power of n digits, where n is the number of digits in the dividend. And this inexactitude might seem quite problematic. It could spell doom for engineering, but it doesn't. Here we are in a building. This building is not falling down around us. We've managed to accommodate it. And how did we manage this? What is the size of the observable universe? U. What's the size of the observable universe? No idea. No idea. OK. One day, someone will know. Actually, that's the answer. 8.8 times 10 to the power 26 meters in diameter, which is a lot. That's pretty big. But look at that exponent. 26 decimal places gets you the width of the universe to the nearest meter. And there are certainly more than 26 places in that expression of 1/7. 36 decimal places gets you the width of the observable universe to the nearest atom. And atoms are small. So honestly, 26 decimal places is quite enough. You might get some error. We can deal with that. Right, what's this value? Now, you might tell me it's 26,998. And you would be completely wrong. Well, not completely. If you assume this is an integer, then yes, it is 26,998. But what I haven't told you is that the lowest 4 bits are reserved for negative powers of 2. So this value is actually 1,687.375. And adding and subtracting these kinds of numbers is simple enough. We don't care about powers in these operations, but let's try some multiplication. Now, if you pass these bit patterns to the multiplier, you get this. And as you can see, this is not 18. This is 288. To get the expected value, you have to right shift by 4 bits. And this tells you straight away that there is some overhead in working in fixed point arithmetic. Since fixed point arithmetic isn't natively supported by C++, you have to manually write a fixed point class. And you might decide to use CPU intrinsics to implement this. And some processors do actually support fixed point arithmetic. But that final part of the operation where you shift the result by the number of bits in the fractional part also highlights another problem, because precision falls away with each calculation. Now, simulations. Now, I write games, and games are mainly simulations. They make heavy use of Newton's laws of motion, which involves a lot of multiplication. And it won't take long for your model to diverge noticeably from what the user might expect. The problem we have is that the binary point is fixed at bit 4, which means we have to divide by 16 after every multiplication. And if we wanted more precision, we would have to divide by even greater numbers, which would yield an even greater error. So in the prior example, if we simply left the value alone and shifted the binary point to the left after each multiplication, there would be no loss of error, but we'd soon run out of magnitude. So let's look at another representation of numbers. So in the first line, we are performing addition. We've got 3 decimal places in each number, but the second number has a higher magnitude. And look at the results, because the results of the addition has 4 decimal places. The results of the multiplication has 5 decimal places. So this looks good. We can accommodate the expansion of precision rather more easily than with fixed point arithmetic. Now, rather than keep the decimal point in the same place in the number, what we are doing is storing the number in 2 parts. We have a value and a magnitude. The value part is known as the mantissa, while the magnitude part is known as the exponent. And note what's happening in the mantissa. It's getting longer. If you're working to 4 significant figures, then you have to decide what to do with the remaining figures. You could truncate the value, or you could round to the nearest value. And this is a tricky problem, and this will return to bite us later. So let's try something in binary. Now, we have to make some decisions. Which part is the exponent and which part is the mantissa? And I'm going to choose the bottom 6 bits for the exponent and the top 10 bits for the mantissa. So that gives us this. Now, when we were in base 10, our mantissas lay between 0 and 1, 0 and 10. For this example, I've decided that our mantissa lays between 0 and 1. So looking at the leftmost 10 bits, counting left to right, we have 1/4 plus 1/64 plus 1/512 plus 1024th, while the rightmost 6 bits total 11. And this gives us an exponent of 2 to the 11th power, which is, of course, 2048. This evaluates to 550, and a similar approach to the second value evaluates 0.2890625. I'm using the color coding there to match the bits to the corresponding powers of -2. But we've got a problem, because if we look at the representations, we have this, and multiplying those two representations using standard integer arithmetic won't actually do the job. The process of floating point multiplication is actually quite a task. And the schema I propose does not invite a unique representation for each number. For example, these two numbers are the same. The value on the right has multiplied the mantissa by 4. So the exponent has been reduced by 2, since 2 squared is 4. Also, how does one represent negative numbers or negative powers? And that would cost a single bit of resolution for the exponent and mantissa. And another problem is interoperability. How do you communicate to your clients how wide the exponent and mantissa are? What if you're exporting a library to some anonymous third party? How do you identify your choice of rounding algorithm? There is plenty of room for error, and this sounds like a job for standardization. So IEEE 754 is what you're looking for. The standard was first published in 1985. Who was alive in 1985? Some of you, indeed. Fewer and fewer every conference, it seems. I'm not killing people, by the way. It just happens. It's coincidental. It's undergone some revisions since then. In fact, the C++ standard refers normatively to document ISO/IEC/IEEE 60559:2020, of course. And this is ISO importing third-party standards into its ecosystem. It's the same thing as the latest revision of IEEE 754. You don't need to read this standard. You can simply rely on your vendor implementation to be conformant. This is my straight face. Indeed. Thank you, Hannah. Anyone play this? Yeah, good. Some people, good. Again, fewer every conference. It's disappointing. So I worked on this. I was the... Thank you. Oh, really? Stop it. No. It was years ago. It was 20... God, it was 20 years ago today. No, it wasn't today, but it was, yeah, over 20 years ago when this came out. The thing is, we started this in 2001. It was actually released on the 10th anniversary of the first broadcast of the first episode of Friends. Anyone here watch Friends? Okay, still relevant. Good. All right. And it featured multiplayer action over the internet, which was quite hard to achieve because there were many megabytes of state, which had to be synchronized with each player at 10 hertz. Now, that's quite a big ask of the internet even now, but back in 2004, it was lunacy. Even transmitting the data from tick to tick was infeasible. The only thing we could do was transmit the commands that were issued to the simulation of the world to each agent and update each agent's simulation equivalently. And this was a really tricky problem. It was very easy to write code that was not deterministic. Now, you might forget to fully initialize an object, and you'd get stale data from the stack instead. You might pass a reference to an object to the camera and inadvertently change things locally. There was just so much stuff that could go wrong. So we devised programming guidelines, debugging strategies. We locked everything down, and it served us well for 2 decades. It continues so to do. But Sega, who publish all the Total War games now, they're very keen to see a console version so that Xbox and PlayStation and even Switch players can join the fun with PC players. And now, it would be quite feasible to have Switch players playing with other Switch players, or Xbox players competing against other Xbox players. But no publisher wants a fragmented audience. You should be able to connect to a lobby and play with anyone at all. Just do it. Just do it. That's basically what publishers say, because publishers are not engineers, they are publishers. And you might be thinking, well, crossplay is a thing. You might have heard of crossplay. And that only works because crossplay is doing very simple stuff. You know, you're not flinging megabytes of state around hither and thither. And you might go on to think, well, won't the same code work the same way and yield the same results on different platforms? We've got a standard. That's what it's supposed to do. 2 + 2 is always 4, isn't it? OK, that's not quite true. You know about the butterfly effect. If you make one error, everything goes wrong quite quickly. How many engineers do we have here? OK, all right. Well, the rest of you, thanks for coming. I hope you're still keeping up. I have a simple example here. Who's heard of Compiler Explorer? OK, good. All right. So I've got a simple example here, 42 lines of code that explain what's going wrong. Unfortunately, we don't have internet here. So, right, there we are. Wow, this is a big screen. OK, all right. Things start to go wrong at the very first calculation. Let's see if this spotlight pointer works. Whoop. Oh, look at that. Brilliant. Things start to go wrong. Oh, where are we? There. Now, up here, I've got all the bits from all the operations. This is really hard. I've got all the bits from all the operations written out here, and basically they start to diverge at distance, which is our first calculation. So here we've got the we've got the NVIDIA compiler here. That gives us a number ending in 7. We have the Clang compiler here. That gives us a number ending 9. Much sadness. Much sadness. All right, come on. There you go. There we are. Let's get rid of that cursor. You'll also see that proj vector y is divergent as well. And this is a real problem, and I want to focus on reproducibility across implementations. So we're going to talk about standardizing non-integral arithmetic. The IEEE decided to standardize floating point arithmetic 1985. Then the IEC thought, oh, we'll have that, and they imported it in 1989. The British Standards Institute in 1990. IEEE said, you know, this is great. Let's have another version. Let's revise it. They did that in 2008. So this bunch of people went, oh, great, another version. And then they did another version in 2019. Yeah, indeed. I'm hoping that's the last version, but time will tell. So this is where we are now, BS, British Standard, ISO/IEC, 60559:2020. Learn that number. If you say it enough times, which I certainly have done over the past year, it will just roll off the tongue. So I'm going to stay current and focus on the latest version. So the standard specifies formats for binary and decimal floating point data, addition, subtraction, all of those things, conversions between different formats, floating point exceptions and their handling, including data that are not numbers. And I'm going to do some foreshadowing here. There we are. And I'm also going to highlight parts that aren't especially relevant to portability, which is those. So in the section on definitions, abbreviations, and acronyms, there is some more foreshadowing. So this is fairly mundane. Language defined. Behavior defined by a programming language standard supporting this standard. That's what you expect. But implementation defined is not. Behavior defined by a specific implementation of a specific programming environment conforming to this standard. So this suggests that this standard is already aware that implementations may differ of the same language. And this, as I've said, is the problem that we're having. Now, onto the meat of the standard. I'm going to rush you through this because, you know, you could try reading it yourself. It's actually quite an easy document to read. It's about 4 hours, 2 glasses of wine, a rainy afternoon. Do you have rainy afternoons in Poland? OK. Next rainy afternoon, read the standard, 2 glasses of wine. Anyway, 3 binary formats and 2 decimal formats are defined in clause 3. There are 11 clauses in total. On the binary format, because C++ only works in binary, we have this one, which you may be familiar with, single precision, and this one, double precision. And that's it, 11-bit exponent, 52-bit mantissa, and 1 bit for the sign. So it's time for our first piece of implementation and language-defined text. The choice of which of this standard's formats to support is language-defined, or, if the relevant language standard is silent, or defers to the implementation-defined, hi. There we are. The names used for formats in this standard are not necessarily those used in programming environments. So back here, they call this binary 64 in IEEE, but we call it double, if double conforms to binary 64. Now, the standard then goes on to tell us what I said earlier, that floating point arithmetic can only represent a finite subset of the continuum of real numbers. Consequently, certain properties of real arithmetic, such as associativity of addition, a plus b plus c, is not the same as c plus b plus a, unfortunately. They don't always hold for floating point arithmetic, so order of evaluation matters. So that's clause 3. Now, clause 4 deals with attributes and roundings. Attributes are associated with the program block. There are 2 different kinds of attributes. Some change the operation of functions. Some are implicit parameters. Rounding falls into this category. There are 5 rounding modes. 5. There we are. Rounding is a beast. During the production of Rome Total War, as we were trying to achieve determinism, we would find that desynchronization would occur on machines with different graphics cards. And it turned out that one graphics card driver preferred a different rounding mode. That's fine. So when you executed code from the graphics driver, it would change the rounding mode. And then it wouldn't change it back. So all of the well-behaved graphics drivers, they keep things nice and clean for us, but one didn't, and this caused divergence. It made me very grumpy indeed. Clause 5 is where things get meaty, because nearly a quarter of the document is taken up with this clause. The standard is quite comprehensive, identifying the set of functions that shall be added by a conforming implementation. Particularly, we have rounding functions. We've got next and previous functions, log functions, arithmetic operations, everything that you can imagine. The usual arithmetic, of course, but also square root and fused multiply add. And this is where things become problematic. FMA computes x times y plus z, rounding only once to the destination format. And it differs from a multiplication followed by an addition, because this would yield 2 rounding operations. Remember what I was saying? When you multiply things, they get bigger, and you've got to truncate them. Every time you truncate, you lose some precision. With FMA, you only get 1 rounding, but with regular calculation, you'll get 2 roundings. That's where the problem lies with FMA. Let's go back to Compiler Explorer for our example. And so you can see where the problem is. Right, there we are. Oh, spotlight. There we are. Right, FMA. At this point, we're calling an FMA. That's 1 rounding. But over here, there is no FMA at all. And so, sadness. You won't always necessarily see a different result. You know, a half times a quarter plus 3/8 will always evaluate the same way, because there's no rounding required. They can be represented perfectly. But sometimes, unfortunately, there's a bad word in deterministic evaluation. Because the compilers are free to choose how to implement these expressions. They can reorder within an expression statement as appropriate for the optimizations chosen on the command line. And you'll note here that none are chosen. This is all just, the compiler options are empty. But we can resolve this by breaking the expression statement into single computations. If you move everything into a single operation and then put a semicolon, then we do get some. We do make some progress. It's not quite problem solved though, because when we switch optimization on, it's anybody's guess. And who wants to run an optimized game? It's not a thing. But we've witnessed all sorts of divergence with different optimizations, and it's not a sufficient solution to merely break down all the expressions, but it's a start. There's a truckload of stuff going on here, frankly. There are conversion operations, sign querying, negation, different types of rounding, ordering, comparison. One day I'll do a full walkthrough of the standard and what it means. This is not that talk. If anyone's familiar with the Goldberg paper, you'll be surprised what else there is. But we'll rush on for today. But yeah, the Goldberg paper on what every programmer should know about floating point arithmetic, absolutely worth reading. So infinity is a remarkably simple concept as far as the standard is concerned. You can do anything with infinity, you get infinity, and it's also signed. But nans, not a number, are really quite subtle, because you can use them for initialized objects, or loudly signaling invalid operations, or quietly signaling exceeding range, or generally identifying that something has gone wrong. Nans propagate, because once your program has gone wrong, it can't be recovered with valid data. So nan takes advantage of representation rules, because not every bit pattern represents a valid number. I haven't gone into depth on encoding. It's an interesting field. The sign bit might seem trivial, but there are some interesting edge cases. How do you choose the sign of 0? I'll leave that for you. Clause 7 talks about exceptions. So invalid operations, square root of a negative number, for example. And there are some things you can't do with infinity. You can't multiply it by 0. You can't divide it by infinity. Division by 0 actually gets its own exception, and so does overflow. And when a result can't be represented by the target's type, this is the thing that gets thrown up. And underflow happens when a result is smaller in magnitude than can be represented. So a number between 0 and the smallest floating point number will generate an underflow. An exact happens if no other exception is raised, and the result differs from what would have been computed with both exponent range and precision unbounded. And this is a matter of magnitude. Clause 8 also talks about exceptions. Clause 9 describes some extra nice-to-have operations like trig functions. Next is Clause 10, and here's where things get interesting. So in Clause 5, we looked at how to perform a single operation, and Clause 10 opens with a summary of Clause 5. Clause 5 of this standard specifies the result of a single arithmetic operation. Every operation has an explicit or implicit destination. For numerical results, one rounding occurs to fit the exact result into a destination format. That result is reproducible in that the same operation applied to the same operands under the same attributes produces the same result on all conforming implementations in all language. And that is a bold statement. All conforming implementations in all languages. Language standards define syntax for expressions that contain multiple operations or combine them. So as we saw, A times B plus C times D. The order of evaluation of operations is relevant. This is a rule for expression evaluation. The formats of implicit intermediate results, and when assignments to explicit destinations round once and rend twice. This is the FMA problem. And this is all a little exciting to me because the implication seems to be that if you write your code using single operations rather than expressions and write your own maths library, then you're golden. But I'm not saying that's trivial, but it's not impossible. And if you remember, I worked for 6 impossible things before breakfast. Now, the final clause, Clause 11, was added to the first revision of the standard in 2008, and it is entitled Reproducible Floating Point Results. This is the shortest clause in the standard, and tempting as it is to read it out in its entirety, I'll summarize because it describes what the reproducible operations are, which is basically all the ones that do something to inputs legally. It describes a reproducible status flag and a reproducible format. But significantly, it defines a reproducible attribute, which is an attribute that is required by a language standard in all implementations. And the clause goes on to say any conforming language standard supporting reproducible programming shall support the attribute, support a reproducible format, and provide means to explicitly or implicitly specify any sequence of reproducible operations on reproducible formats supported by that language. And it shall also explicitly define a whole bunch of things, including reproducible results attributes, which indicates when reproducible results are required and when they are not. So you can switch it on and off whilst in the program. The final part of the normative standard instructs users how to obtain the same floating point numerical and reproducible status flag results on all platforms supporting such a language standard. And it's a list of programming guidelines, just as we had 20-odd years ago. 5 do's, 9 don'ts. And this came as a bit of a surprise, because typically implementations are 60559 compliant, aren't they? Which means that specifying the reproducible results attribute in code should be all we need to get what we want, which is portable, reproducible, floating point operations. Why has no one told me about this yet? Well, let's see how the standard does specify floating point behavior. Standardizing C++ for non-integral values. You might find this a slightly sarcastic section title. Is anyone here sufficiently familiar with the standards to be able to tell me where floating point behavior is specified? Seems unlikely. OK, let's go back to the browser stuff. We'll start with basic.fundamental, paragraphs 12 and 13. So we have 3 distinct types, float double and long double. They can represent floating point numbers. Wow, this is a long way up. The type double provides at least as much precision as float. Long double provides as much. So what they're saying is floats are contained by doubles, which are contained by long doubles. The types are collectively termed standard floating point types. And an implementation may also provide additional types that represent floating point values and define them as to be extended floating point types. The standard and extended floating point types are collectively termed floating point types. So this is the C++ standard. It's full of this lengthy, legally stuff. It has to be precise. The The final paragraph is a bit worrying. Except as specified in basic.extended.fp, the object and value representations and accuracy of operations of floating point types are implementation defined. So, yeah. I felt a sickly panic when I read this, and I went scurrying to basic.extended.fp to see what was on offer. So this is what's on offer. And it simply says you can define a type that matches binary 16 as defined in IEEE 754, and also binary 32, binary 64, binary 128. There's another one called bfloat, an AI float type. But again, it tells you nothing about operations, accuracy, precision, nothing at all. And it turns out that C++ has almost nothing to say about floating point arithmetic. It's really quite casual, and the reason for this is that not every implementation platform is IEEE 754 compliant. If the standard started mandating compliance with IEEE 754, or more particularly 60559, then suddenly we would have a whole section of implementations that were no longer compliant with C++. What to do? Now, this is a less sarcastic heading because C is also defined for platforms without IEEE 754 compliance. And again, there is nothing mandating floating point behavior, but there are some annexes to the C standard which help us out. More than half of the references to 60559 in the C standard are actually in these annexes. Let's take a quick look. Annex F spins through 60559 in much the same way as I described it earlier. C23 defines a macro called this, stood C IEC 60559 BFB. If an implementation defines this with the value of that, that means that the implementation conforms to the specifications in this annex for binary floating point arithmetic. Annex F goes on to cover a lot of 60559. It provides mappings for names. So, for example, binary 32 in 60559 is named float. In 9899 is the number of the C standard. Binary 128 is named long double. Sometimes symbols are used. So compare signaling not greater is not x greater than y. Compare quiet not greater actually is a name, is greater. Sometimes cases are changed. So next up, this is the IEEE name, the 754 name, gets called next up by C because of snake case. Annex F works its way all through. And it makes changes to names, introduces symbols, adds identifiers for functions to carry out behaviors. You can't just say, apply everything in 60559 and walk away. You have to actually spell it out and modify according to the prevailing standard and drafting rules, for that matter. Annex F9 covers optimization. This section identifies code transformations that might subvert IEC 60559 specified behavior and others that do not. And there are statements about code removal, code motion, expression transformations, all of this sort of stuff. And the rest of the annex looks at math.h and tgmath.h. Annex G looks at complex arithmetic, and Annex H looks at interchange and extended types beyond float, double, and long double. But wait, I hear you cry. Wait, indeed. What about ISO IEC 60559 Clause 11, reproducible floating point results? Well, what indeed? It doesn't feature at all. They just don't mention it at all. I think, I probably need to talk to some people who've been on the standard committee for a long time, that reproducibility was introduced in 2008, but the C standard at that time was just coming up for revision. And no one's done it, no one's proposed it. You know, if you don't propose a thing, it doesn't get in. If anyone's ever heard of allocate unique or make unique was added 3 years after we had unique pointer because we just forgot. We had make shared, but we didn't have make unique. This is what happens. Optimization. So fusion and reordering are the two methods of optimization available to the compiler. As we've seen, FMA can be problematic. Reordering is not an option for reproducibility either because of the characteristics of the processor being targeted and how it's not associative. How do we overcome reordering and fusion? We basically have to rewrite the code and put semicolons everywhere. But the trouble is, it's ugly. Now, MSVC does have some floating point options. FP fast, sounds like it's for optimizing, and it is. But it moves stuff around. It's absolutely not reproducible. Precise is the default compiler behavior. The compiler preserves the source expression ordering and rounding properties of floating point code. It's much more, but it's slow. It is so slow. GCC has things like float store and fno-math erno and unsafe math optimizations and no trapping math. Again, finer grained control of the floating point environment. And all of these will change the behavior. And these are the things that often guarantee faster performance of floating point code. And then fast math, which basically turns all of these on. So if we turn off all math optimizations with single operations for expression and write our own math library, are we golden? Now, I don't know about you, but one of the reasons I like using C++ is operator overloading. The ability to build complex expressions that look like they've come out of a textbook. They're easy to understand. They do what they're supposed to do. When I started programming, which was in the 1980s, who was alive in 1980 when I started programming? Great. Again, fewer and fewer people. This is aging. This is you lot in 30 years, okay? But they're easy to understand, operators. It's just like a textbook. I had an awful time putting math functions together in the 80s. Honestly, it was, oh, have I really got to do things one step at a time, is what I'm thinking to myself. There's got to be a better way, and I have some ideas. So, improving reproducibility of non-integral values. Oh, I've got 10 minutes left. What do you mean, 5 minutes, young lady? It says 10 over here. But anyway, this is what we're doing as a first crack at 6 impossible things before breakfast. We've got a geometry template library. It takes an arithmetic type as a parameter. Currently, we're defaulting to float, and it's working fine, but it's not deterministic. What we need is a type that can be taken as a template parameter to our geometry library, exhibits floating point-like properties, so exponents and things like that, is reasonably precise. We don't need it to be thoroughly precise. We just need it to be consistently precise across all platforms. As fast as possible. Obviously, we're making games. Hang on. I missed something out here. We can actually do better. We can try changing the standard. Now, that class from the prior slide isn't going to fly in the standard. It's extraordinarily specific insofar as it sets aside 60559. So, no, that's not good. What we want is some way of preventing reordering. Now, one idea that's been floated internally to my employers is the idea of having fences, like memory barriers. But that becomes terribly unergonomic. It would greatly reduce the legibility of the source. An idea I had recently was a new attribute, reproducible, which would identify a function as being immune from floating point optimization. And this would also advertise to the linker that link time optimization was not available for the function. But it's still a function qualifier, like const. You can qualify functions by const. And one problem with such a function, though, is that it must not call any functions which might affect its reproducibility. So this is quite a complicated bit of analysis that needs to be performed at compile time. And the same problem arises with the idea of pure functions. Anyone heard of pure functions? They're great. Pure functions are functions that you just execute them and they have no outside context to worry about. So they're eminently threadable. We don't have pure functions in C++. It's been proposed. We do suddenly have pure functions in C, only they're called unsequenced functions. And another thing they've done is they've snagged the keyword reproducible. So we need to come up with something else. In committee last week, we reviewed my paper, P3375, reproducible floating point results. It's pretty simple. I define this enumeration and this class. And the class defines operators, but specifies that execution behavior of operations on objects of type strict float shall preserve the literal meaning of the source code. Operations shall not be reordered or fused. Don't take the wording too seriously. The paper was well received, but there is little appetite for adding yet more overloaded operators into the STD namespace. In my next revision, I'll simply propose the functions which the operators implement, and in this way, the user can build their own version of the class. There's another paper in the same sort of space, and this proposes rather drastically deprecating these two functions, fesetRound and fegetRound. Anyone here use fesetRound or fegetRound on anything more than an occasional basis? Brilliant. That means it's probably a ripe candidate for deprecation. And we replace them with a struct called struct rounded, which represents the rounding mode. And then we have static functions bound there, which will do add, sub, multiply, divide, FMA, square root, defined as binary functions. They're all carried out with the rounding mode passed to the constructor of the type. But neither of these papers are near complete. Things might not look great for C++26, but there's always C++29. But there is actually a larger problem, which is controlling the floating point environment. It's a mishmash of mechanisms, because first we've got command line options like fastmath, and these are set before the compiler even starts to execute and stay in place for the entire duration of the compilation process. Then we've got preprocessor pragmas like hash pragma stdc fp underscore contract. And these are set before compilation starts during the pre-processing phase. And finally, we've got C library functions, such as fegetRound. Some of these are set at compile time, and some are set at runtime. Some are modified at compile time, and so on. And these come from properties described by 60559. And these mechanisms date back to C, but what we can do now in C++ is use const eval functions to execute things at compile time and compile time only. So this gives us opportunities for much finer-grained control of the environment, testing if an attribute is available during the compilation stream, and then compiling code paths conditional on that availability. Template metaprogramming, I'm sure some of you have tried that out. It's quite a tricky problem, though. I was speaking with Hannah yesterday about it, and it's not as easy as I thought. You'll be hearing from Hannah later in this room. Do go to a talk. It's great. Thank you, Hannah. But I hope to bring this paper to the next committee meeting. That's in Hagenberg in Austria on February the 10th. For any of you who fancies joining the committee, we need more bodies. It's an entirely voluntary effort. Anyway, this is where we are at the moment. I showed you how humans and digital machines deal with non-integral values, and then we looked at how this idea has been standardized, how we incorporated that into our standard, and finally, I wondered how we can improve on this, taking us towards portable floating point calculations. Thank you. Ask me 2 questions. 2 minutes.
Thank you so much, Guy. And let's do that. 2 questions, please. So question number 1, over there, please. Thank you. Lovely.
I have a question. Maybe I just didn't catch it during the presentation.
It was quite fast.
Yeah, it was very good also.
Oh, thank you.
How did you actually manage to provide this simulation coherence on those different devices in the game you were describing earlier?
It was the same binary.
Okay, so...
Same binary running on x86 processors. So that level of similarity is sufficient.
Okay.
But for example, on the PlayStation, you're using a different compiler.
Mm-hmm.
So that will give you different, entirely different characteristics. Some compilers are quite happy to put FMA in place. Other compilers aren't. You need to coax them a bit more. And the problem that we have is that things on the command line, for example, are vulnerable to different versions, changing the way that things work. So it is quite a deal creating a reproducible environment on a compiler. I'm not going to say it's impossible, but it's impossible.
Okay, thank you.
One more question, please. One more over there, please, the second row.
Run! Run! Come on, down the stairs. Imagine there's a Roman legionary after you with a javelin. Ah, safety's for... Actually, no, safety is for C++.
Yep, got it now.
All right, then, yeah.
Hello.
Oh, hello.
Great talk.
Thank you.
Are there any tools like we have UBSAN and ASAN, maybe some
Yep.
FPSAN to detect that something bad is happening, something that could be not reproduced on other machine?
You're going to have to ask me that again. I'm sorry, I wasn't paying enough attention.
So
It's
we
been
have
a long week.
we have different tools to detect, let's say, undefined behavior.
Yes, yes.
So are there any tools that detect operations on the floating points that could yield different results on different architectures?
I don't know of any tools. If anybody does, do get in touch with me. Unit tests, yeah, unit tests would be great. In fact, one of the big problems with reproducibility is in the finance industry. You write some code, you write some unit tests, and then the unit tests work fine on your Windows platform. You then take those unit tests onto Linux, and the unit tests fall over. And that can be really a problem for an industry that's heavily regulated. You've got to then come up with all sorts of regulatory sort of workarounds. Honestly, the finance people, the banking people, they were biting my arm off when I said, hey, do we want reproducibility? Yes, we do. Oh, maybe you give me some money. No, we won't. But it's the thing they want. This is the thing. It's a voluntary organisation. The committee is made up of volunteers. We're not hand-selected by our brilliance. I'm not brilliant. I'm just enthusiastic. All hands to the. Do think about joining. Do think about helping. Poland's full of great engineers. I'm sure we could use your help. Tools, no. Unit tests, they highlight the problem. Anyone who wants to write some tools? That'd be great. Got 1 minute.
So I'm going to say, Guy Davidson, thank you very much.
Thank you very much.